All right, everyone, let's settle down. I guess we can go ahead and get started um, for today. Before I do that, quick announcement about homework 10. Those of you who just saw my email, uh, the area of cross section for problem 2 and 3 was missing in the problem statement, so just sent out an announcement about that. Has anybody tried homework 10 as yet? Okay. Not too many people looks like, but that's so for homework 10 I will quickly point out that for problems 1, 2 and 4 you should not have to change any of the MATLAB code. You can use that MATLAB code, you just have to write new input files, explain your work, uh, and basically MATLAB would do all the computations for you. For problem 3, where there is a frame with an inclined support, you actually do have to change the MATLAB code that's given to you. And those changes would be extremely similar to what you had to do for the truss problems back maybe 3 or 4 homeworks back. But this time I'm not giving you a template code where to make those changes. So I'm hoping that you can figure out what MATLAB needs to compute and how you can create those matrices. It would be extremely similar again to those stress problems, so hopefully it should not be a problem. But again, if you have questions, post them to the discussion forum. Any particular questions about the homework or the lectures that we've been talking about? No? All right, so what I'll do today is finish out this example of the frame problem that I was doing last time with a lot more detail. And that would be also the type of detail that I'm expecting from you on the homework 10 when I ask you for quote unquote write or screen capture from MATLAB these steps of those computations. Uh, so if you have any questions about these types of problems, let me know as we go along. So last time we were kind of in the middle of doing this problem, this portal frame with an inclined roof. Uh, we all understand this, how this input file works. Um, what I will point out is that the first step that we do is we calculate the element stiffness matrices for each element in its local coordinate system. So this right here is, for example, for element 1, where the local coordinate system, of course, is oriented along the element. We cannot use this element stiffness matrix in its local coordinate system. We cannot assemble those local element stiffness matrices because for element 2, those coordinates are pointing in a different direction. For element 3, they are yet another different direction. For element 4, of course, in a different direction. So the first thing we do is to transform this local coordinate system to a global coordinate system. This purple x prime y prime to this blue x and y. This blue x and y coordinate system is the same for each element. And let me ask you this: how do I do this transformation from k element local? And maybe even should I step back? How do I first of all calculate this k element local? How do we calculate that? This is for a frame element with 2 nodes, 1 and 2. How do we calculate k element local, this 6x6 matrix? Go ahead, Ivan. The, the element stiffness matrix that we derived, yes, by combining the truss and the beam matrices, right? So it's this 6x6 matrix. No matter which way the element is oriented, it will always be this 6x6 matrix for a frame element. So we allow MATLAB to compute all these numbers for us, and hopefully, well, a quick check, of course, would be that the zeros are in the right positions. Let's check. I think I just need to stay here. Example. So, yep, zeros out there in the second, third, fifth, and sixth columns of the first row, and so on. So that's the local element stiffness matrix using the formula that, or using the expressions that we developed. MATLAB computes that very easily. And then how do I transform it to the global coordinate system? How do I transform this to the global coordinate system? The transformation matrix that looks like two transformation matrices for each node and on the diagonals. So that was this procedure that we talked about. Uh, you are converting your local degrees of freedom to global degrees of freedom using this element transformation matrix, which has these two, and I think I had corrected these two diagonal transformation matrices. So again, MATLAB would be able to calculate this very quickly for me, just doing a T times K times T transpose. MATLAB would do that very quickly for me. And that's how we get this new 6x6 matrix. Note again that because this element is oriented in the vertical direction, the conversion from this local coordinate system to global coordinate system is not that complicated. You are just shifting some elements or shifting the components to their correct locations. So for example, x prime here is same as y in the global, and y prime here is same as minus x in the global. And that if you go through the rows and columns of these matrix, you can convert without having to do that 6x6 multiplication 3 times very easily. But for the inclined elements, yes, it's much more complicated. We allow MATLAB to do those computations. This vertical member, element 4, is again slightly different from element 1. Note, because element 1 local coordinate system points from node 1 to node 2. So x prime is oriented in the vertically up direction, whereas for element 4, it points from node 4 to node 5. So x prime points downwards in the x prime direction. Okay?
That's mainly because of our notation for the nodes.
That is indeed because of the connectivity that we had defined in our input file. We are saying 1 is connected to 2 and 4 is connected to 5. If we switched the order, 5 is connected to 4 here, the problem would still work. The program would still work. It would give you the correct result. It's just that your uh, your K global stiffness matrix for element 4 would turn out to be slightly different. Okay. Um, So it's these global components that we assemble. We get this huge 15 cross 15 stiffness matrix. I think I had run the MATLAB code also last time to get to that point. I'll do that again. So run, and by the way, this input file name is frame2.txt in the codes that I posted. So at this point, I have this K stiffness matrix 15 cross 15, which doesn't even fit on one page. Uh, so once I have this 15 cross 15 system, these two lines in MATLAB, this 53 and 54, these two lines in MATLAB solve for the global displacement and the global force vectors, which includes reactions as well. And that's what's mentioned on your handout here. So knowing this solution, this is the solution for displacement, this is the solution for reactions. Now the job is to try to draw the axial force, shear force, and bending moment diagrams. That's what I want to talk about. How would you do that? So the way you would do that is to go to each element. You know the displacements in the global coordinates of each one of those elements. You take those global displacements, convert them back to local axes, and then do the local element stiffness matrix times local degrees of freedom. That give you local element forces, and we'll do that. I'll show you along as we do it. So for element 1, it's connected to nodes 1 and 2. What would be the degrees of freedom associated with element 1? With element 1, with node 1, it would be 1, 2, 3. What about element 1? 4, 5, 6 as well, right? There are two nodes. So first 6 degrees of freedom is what we want for element 1. Let me try to get those. So I have these. I should have actually stored all my element matrices. So let me do that. I'll run this code again. Um, so I'll place a breakpoint here. I'll run it again. Choose my input file frame 2. So at this point, K element is the element stiffness matrix for element 1. I'll store it as uh, K1 local is equal to KLM. So that's the element stiffness matrix for element 1. And this is exactly what I'm expecting you to do for the homework as well. But more importantly, you should understand how what's going on in this code. So I'll continue again. Now we are on element 2. So I'll write K2 element is now equal to KL, which is the element stiffness matrix in this is the element stiffness matrix in global coordinates. So I do want to have the local element stiffness matrices. So I think so the easiest way would be to let MATLAB run the plot program, and then I can show you how to do that. All right, let me remove this breakpoint and go to this plot line. Let me run it out to there, and then we'll go inside this plot program. And let me do that again. So run frame 2. Going inside that plot frame with the step in function. So in this program, what this plot function does is it takes the nodes of the entire frame. There are 5 nodes. I know the element connectivities for the 4 elements. I know the Young's modulus for all the elements. I know area of cross section. I know moment of inertia. I know the boundary conditions, loads. These are the same things that we had as the input parameters. But in addition, I also now know the global solution, this U vector that MATLAB had just computed. I know what the solution for the problem is. I know also the F, forces and the reactions at all the points, at all the nodes. So using this information, I should be able to plot the result of this computation. And in this function plot frame 2D, there are sort of these comments that help that should guide you to the right location. So this section is about plotting the old shape. I'm not interested in that. Plot the new shape. How do you plot the new shape, by the way? Plot the old shape is simple. I know the locations of all the nodes. Just connect them with lines. And the commands to do that is already given here. The command that I use is plot in MATLAB. How do you plot the new or the deformed shape? You take the displacements, you add it to the old coordinates, you get the new coordinates of each of those nodes and connect them not with straight lines, but with functions that actually depict these 4 shapes. So you remember for the beam method we had right here. You remember when we derived the beam stiffness matrices, we had these 4 different shapes. These are the 4 different shapes that are used to plot along the length of the element. Each beam element won't be a straight line. For truss elements, it's easier because even the deformed coordinates, the connectivity is just a straight line. But for beam elements, it's not a straight line. You need to take the precise shape of this deformed shape for different cases. And for those of you who are interested, these are, anybody know what type of functions these are? If I were to use polynomials to try to express these functions, these would be cubic polynomials. Cubic polynomials because cubic polynomials have four coefficients: ax cube plus bx square plus cx plus d. A, B, C, D. There are four coefficients, and you have 4 degrees of freedom to which these four coefficients are tied to. So you can solve for those coefficients by imposing that the function should behave in this way. And these, it turns out that these are cubic polynomials, and more precisely, they're called Hermite cubic polynomials. So anyway, this is basically what is used for plotting the new shapes, for which you don't need to be too concerned about. Let MATLAB do all that plotting, plot the loads. It's just going to plot whatever input loads it had, and plot boundary conditions and reactions. Again, you can go through that. And finally, at line 164, we are starting to plot the shear force, bending moment, and actually the axial force diagrams as well. So those would be plotted in figures 2, 3, and 4. Let's see how this MATLAB program does that. So what we'll do is we'll go to this this first part, which is just going to plot the undeformed and deformed shapes. Actually, the undeformed shape, and at that point, what we want to do is to extract. Um, I'll put a breakpoint here, run it up to this point. So once I'm at this point, line number 181, which says plot the axial force, shear force, and bending moment. At that point, you'll be able to see that this part of the code is extremely similar to your frame element 2D code. Frame element 2D code is nothing but calculate the normal vector n hat, m hat, construct the transformation matrix from that, construct the bending part, the axial part, and you have the local element stiffness matrix. That's the local 6x6 that I just showed you. And then you transform that local 6x6 to the global coordinates using this k element, using this transformation. So this plot frame 2D to calculate the shear force, axial force, shear force, and bending moment is also very similar. You calculate n hat vector, m hat vector, transformation matrix, calculate the bending part, calculate the axial part, and now you have the k local for each element. So what I'll do is I'll stop my code at this line number 217, which you'll see in a minute why. Um, and at this point, I am at element 1. So this is the counter for the element II is equal to 1. I'm looking at element 1. I've just calculated its local element stiffness matrix. That local element stiffness matrix is again from that 6x6 that we had derived. I calculate the element degrees of freedom for this element. Since this element is connected to node 1 and node 2, I'll have 6 degrees of freedom, which are 1, 2, 3 for node 1 and 4, 5, 6 for node 2. What I want from the global degrees of freedom, this is the global 15 cross 1 solution that MATLAB has computed, and I want to plot the deformed shape and the shear force, axial force, and so on. From this 15 cross 1, I need to pick out those 6 degrees of freedom. This element degrees, this first 6 degrees of freedom. So this line 217, it picks out, so I'll execute this line. It picks out those first 6 degrees of freedom from this 15 cross 1. Okay. And let me ask you this. Are these U element degrees of freedom, are they in the global coordinates? So I'll write it here. Are these in the global coordinates or the local coordinates? Global, right? And maybe let me try something else here. If I copy this and if I can paste it to that example. So these 6 degrees of freedom are the local displacements for this first element in the global coordinate system. Can I do k element times these 6 degrees of freedom? I can't. I need to convert these 6 degrees of freedom from the global coordinate system to the local coordinate system. How do I do that? Transformation transpose, the inverse transformation, right? So, and of course the MATLAB code would do that for you. You just have to follow along. This is right here, transformation transpose times U element. That gives me U element local. So I'll execute that line as well. And now I have the local degrees of freedom. And since the transformation matrix for this particular element is very straightforward, it doesn't have too many cosines and sines because it's vertical. That transformation just rearranges those degrees of freedom. So let me go back to here and I write U element local, and those are the local degrees of freedom. I'll copy those, paste them to here, and those are now my local degrees of freedom. I can multiply this element 1 local stiffness matrix, this matrix, I can multiply that with this, the local degrees of freedom, to get the forces at the ends of this element. And that's exactly what MATLAB code would do now. So you can see that the K local, that 6 cross 6 multiplied by U local gives me F local. So I'll do that. And I have F local, which so this is the local forces and moments. Once again, I'll copy all of that. And of course, I'll post all of these nodes on Blackboard, so you don't need to worry about copying all these numbers, but make sure you understand the process that we are going through here. Sorry. So that gives me forces. And these forces, maybe I should draw those. So these forces are the local forces and moments in the local coordinates. These are the element forces and moments in the local coordinate system. So what do they look like? They look like Q I x prime. They look Q, sorry, Q I y prime, and a moment mi. Similarly, I have Q j x prime, Q j y prime, and a moment mj. Okay, so if I have these 6 local forces, which are basically right here, Q I x prime, Q I y prime, M I, Q j x prime, Q j y prime, M j. That's the local 6 cross 1 that we got by taking K element local coordinates acting on U element on the local, sorry, not in blue, but in purple, the U element in the local coordinates. Okay. So now that I have these 6 element forces and moments, how do I determine what is axial force, what is shear force, what is bending moment for this element? is this Qix and Qjx prime. Qix prime and Qjx prime. They should be related to axial force, right? So which one is positive axial force? Which one is negative axial force? Right. So Jx prime right here. Hopefully my point. Yeah. So Jx prime is the positive axial force. Um, Let me move that a little bit. So this Jx prime is positive axial force. Qix prime is negative axial force. And maybe we should check the numbers before we proceed. Uh, so negative 10 and uh, negative 10 here. That makes sense, right? The first component here, I don't know if you can see that from back in the room, but this is negative 10 times 10 to the power 3. This is, uh, so this is negative of 10. This is already negative 10. So the axial force in the first member is what? Compressive or tensile? Since the value is negative, it's compressive. And that also makes sense. If I have a load up here, this better be in compression. And since the load total is 20 kips, or whatever that unit is, 10 should be here and 10 should be here. So both of these should be in negative 10 kips compression, which is exactly what we are getting from this. If we take the negative of that value and the positive of that value, we get the axial force diagram, which should be on your handout right here, minus 10,000 to minus 10,000 between nodes 1 and 2. That's how you plot, that's how you find the axial force. Similarly, for shear force, is this Qiy prime and Qjy prime? Which one is positive, which one is negative? So, say it again. I prime is positive because, yes, it is the left end of a beam. And if I have a beam on the left end, shear force pointing up is positive, and for the corresponding section on the right end, shear force pointing down is positive, right? So indeed, Iy prime is positive, Qj prime is negative. So J prime is right here. That's negative shear force, and that's positive shear force. So let's check again. The second element is minus 2.56. The fifth element, Qj prime, is plus 2.56. So indeed, if I take positive of the second element, negative of the fifth element, I get a shear force in this member that's negative 2.56 kips or kilo units. And finally, for the moment, which moment is positive bending moment and which is negative? Mi is negative, Mj is the positive bending moment for this element, right? So indeed, this guy is negative bending moment, and this is positive bending moment. So if I look at element 3 of this is 0, as it should be because it's a hinge at the bottom, and this is negative 5.11. If you look at the deformed shape, it kind of looks like that. And yes, at this point, the moment would be clockwise pointing into the plane, which would be a negative bending moment, right? So indeed, if you look at the bending moment diagram, it starts out at 0 and it goes to negative 5.119 kilo or kip feet, or kip inches is probably what I used here. So that's basically that's the calculation for the shear force, axial force, and bending moment diagrams, which is done automatically by by the code that you have. Once you have the solution, pick out the element degrees of freedom, convert those element degrees of freedom from the global coordinates to the local coordinates using the inverse transformation. take that local degrees of freedom, multiply that or pre-multiply that with the k element local for that the element local stiffness matrix. You get the force vectors and pick out the correct components from those from those 6x1 for the axial force, shear force, and bending moment diagram. Make sense? We'll do that for a couple more elements, and then I'll let the program run through. Uh, so we have this. Um, by the way, these 4 lines here are just to check whether one of those quantities is very small, so you can safely ignore that. Um, and um, and you can see that axial force is negative of the element uh, local first component. What is FEL local first component? From our notation, F element local is this guy. So the first component is QIX prime. That's negative axial force, right? Which is exactly what the MATLAB code also does. It takes the first element negative of that gives me axial force at node 1, and F element fourth component is QJX prime, and the positive of that would give me axial force uh, at the second node of that element. Similarly, shear force is QI prime positive, QJ y prime negative, and similarly bending moment mi negative and mj positive. So if you run through that, I have the axial force at the 2 nodes of the element, the shear force at the 2 nodes of the element, and the bending moment at the 2 nodes of the element. And all that's left to do is to just plot them, which again you don't need to be too concerned about. Uh, so for the second element, so you can see that it's already plotted that for first element. For the second element, um, element degrees of freedom are 4, 5, 6 for node 2 and 7, 8, 9 for node 3. The second element is connected to nodes 2 and 3. So we pick out those particular 4 to 9 degrees of freedom from the global vector. We convert them back to the local coordinates, calculate the uh, calculate the force by pre-multiplying it with its local element stiffness matrix, and once again we pick the for the axial force, shear force, and bending moment diagrams, we pick the negative QIX, negative QJY, QJY prime, and negative of MI. So if you do all of that, for the second element, we find that the axial force is negative and constant through the element. Um, and similarly for the shear force is also constant positive, and bending moment is varying linearly from negative to positive, which if you look at the deformed shape, that should be visible. This element, it has a frowny face curvature at node 2 and a smiley face curvature at node 3. So indeed there should be a point of inflection in that element, because here I have a negative bending moment, here I have a positive bending moment. So of course, if you look at the bending moment diagram, it goes from negative to positive. Okay. All right. So you can proceed with all the rest of the elements in the same way, and that's basically how we calculated all these shear force bending moment diagrams. Any particular questions about this before I let the code run out? So I'll remove the breakpoints and let it run through. Right. And the numbers gets crunched up, but again, you can zoom in and visualize. So essentially what I'm asking you to do is to understand this process and exactly like what I have in my notes. If you look at the discussion forum also, I posted a hint about this of looking at page 22. Let me see if I can pull that up. Nope. Sorry. Example. Thought I had this example, but even last time I wasn't able to find it. Hmm. Right. So for the frame or the beam problems, what I expect you to do is to tell me how you got what would be the local element degrees of freedom, pick them out, calculate, transform them if needed. For beam problems, you of course don't need to transform them, everything is horizontal. K element local would be the same in the local or the global coordinates. Pre-multiply by Ka times Ua, get Qa, and then interpret those quantities in the correct way to draw these shear force and bending moment diagrams. Okay. All right. Um, in the 10 minutes that are remaining, let me quickly give you an overview of three-dimensional problems, which will not be on the exam again. But again, I'll give you the code. You can use it whenever you need. This is from the handout that I gave you last time. Um, the benefit of all of this stiffness method is that it's exactly the same procedure. Doesn't matter how complicated your structure get. Doesn't matter how whether it's 1D or 2D or 3D. It's the same philosophy. So if you can generalize this method from 2D to 3D, then you can very easily solve complicated trusses, which are definitely not easy to solve by hand, right? So here's the logic behind these truss problems. And if you are wondering what a three-dimensional truss looks like, this is an example, right? This is fairly complicated structure. The dashed lines are the original configuration. The solid lines are the deformed shape of that truss. So the key extension that you should understand for three-dimensional trusses, of course, each node now has 3 degrees of freedom in the x, y, and z. But the behavior of each individual truss element remains exactly the same. Each element can either be in compression or in tension. No other possibility, right? So the key difficulty, or maybe the complication from going from 2D to 3D, is how do you transform local degrees of freedom to global degrees of freedom? Now, because if you remember from the 2D case, what we had to do was compute the local element stiffness matrix, which was that 4 cross 4 with 1, -1, -1, +1, very simple. Now, the local stiffness matrix would be 6 cross 6, still remains simple, but you have to convert it from a three-dimensional coordinate system that is oriented in some arbitrary direction to nice XYZ. And there is a very systematic way of doing that. And if you try to memorize those formulas, it would be very complicated. But if you understand how this is working, let's see if I can explain that. So here's the logic for this. To convert a vector v, which again is a physical quantity, it does not depend upon a coordinate system. This vector v can be expressed in both coordinate systems. It can be expressed in the global x, y, z, and in the local x prime, y prime, z prime directions, right? Its expressions, it would have three components in both of these coordinate systems. In the global, I would have, say, components v1, v2, v3. In the local coordinate system, it would have v1 prime, v2 prime, v3 prime. They are both the same vector. They are both mathematical descriptions of the same vector, but in two different coordinate systems. The problem is, how do I relate these components to these components? You remember how we did that for the 2D system? How did we relate V1, V2 to V1 prime, V2 prime for a 2D problem. Yeah, we drew sort of this geometrical construction. Yeah, we drew this geometrical construction, found out its components, and using trigonometry, we said, well, some components are cosines and sines, and we came up with these expressions. For 3D, it's very complicated. That's maybe not the best approach for using trigonometry in three-dimensional space, right? So here's the logic that we'll use. We'll take the vector uh, we'll take the vector in the local coordinate system with the primes, and I'll take a dot product of that vector with unit vectors in the local coordinate system. Okay, so if I express, say for example, v1 prime dot with e1 prime, what would if I take this vector v, take a dot product of that with the unit vector in e1 prime direction, what would that be? A dot product of two vectors is, let me ask you a simpler question. If I have a vector with components 1, 2, 3, okay, and if I take the dot product of that vector with the unit vector I have ijk, for example. So if I take dot product of 1, 2, 3 with unit vector I, what do I get? 1. If I take dot product with j, 2. Dot product with k, 3. So dot product essentially picks out the component of one of those components. If I take dot product with E1 prime, I pick out V1 prime. Dot product with the E2 prime, pick out V2 prime, and so on. So if I take the dot product of that V with one of those unit vectors, and I also take the dot product of these guys with E1 prime, I would get something that looks like V. Maybe I'll write that out here. I would get V1 E1 dot with E1 prime. So this is V1 prime is equal to plus V2, sorry, E2 dot with E1 prime, and finally plus V3 E3 dot with E1 prime. And what it shows me is that how is V1 prime related to V1, V2, V3? It is related to them in terms of dot products of these unit vectors with themselves, right? So if you look at this picture, I'm taking the unit vector E1, which is along global X, taking a dot product of that with unit vector E1 prime. So those are two vectors. If I take a dot product of those two unit vectors, it's going to be what? It's going to be what? It's going to be the cosine of the angle between those two, right? If I have two vectors, if I take a dot product, that's A times B times cosine theta, theta being the angle between them. So essentially, this this expression helps me do trigonometry in 3 dimensions. It's just taking the cosine of the angle between E1 and E1 prime, cosine of the angle between E2 and E1 prime, E3 and E1 prime, and all of these cosines end up being coefficients that I'm calling Q. These cosines are all numbers between 0 or -1 and +1. So these numbers, I will store them in a matrix, which happens to be the transformation matrix in 3D, which we can very systematically calculate by uh, taking cosines between all possible pairs of these unit vectors, and then using that transformation matrix, I can conduct all the rest of my calculations in exactly the same way that we did for the 2D for the two-dimensional trusses. One additional change is that the local element stiffness matrix for three-dimensional truss elements is now 6 cross 6. It's 6 cross 6 because there are 3 degrees of freedom per node. And the structure remains exactly the same. We have 1, -1, -1, 1. Everything else is 0. The uh, the coefficient out there is still AE over L. So, which also makes sense because if you look at a truss element, if you look at this truss element, the only thing that would contribute to compression or tension at in this member would be displacements along x prime at I and j. Displacements along y prime or displacements along z prime are not going to cause any tension or compression as long as the displacements are small, right? So that's why we have all of the rest of the rows and columns zeros. So we take this 6 cross 6, that's the element stiffness matrix, pre-multiply by the transformation transpose, transformation times element local, which is this guy, times transpose, exactly the same way that we did for the 2D cases. That gives me element stiffness matrix in the global coordinates, which I can then assemble for all of my truss elements in the problem and solve it as usual. Okay. Did you guys solve a problem for the method of joints for three-dimensional truss on one of the homeworks? Right. So, so I think some of that you already should have seen, but of course you've not seen how to do the transformation in 3D. But now, hopefully, if you go through this exercise, you'll see how to do that. So very quickly, I'll run through an example here. This is an example. Let me also explain a key feature of the input files for three-dimensional trusses as well. In this example, I have this three-dimensional truss. Looks complicated, but on the base, I have these 4 nodes. Okay, so let me point them out. I have these 4 nodes on the base, and I have 4 nodes on the top, and I have lots of connectivity between all of these all of these elements. So I will definitely have more elements than equations. So this is a highly indeterminate truss. Um, Now, there are some point loads also given. There are these 8 nodes, as I mentioned. First 4 are on the base. The next 4, 5, 6, 7, 8 are at a height of 1. The element description is a little more complicated in 3D because what we are saying is that element 1 is connected to nodes 1 and 5, and there is 3 long numbers, and then there are this 1 and 1, which is just the Young's modulus and the area of cross section. So these 3 long numbers that I have here, what they define is the orientation of the element. So for example, in 3D, if you have, let's say, a truss element that's made out of W shape, for example, W shape has some orientation, right? If you look at the cross section, it has a major axis and a minor axis. So what you need to specify is which orientation do I have in 3D, because that becomes important. Um, Not for truss problems, but for beam problems, it becomes important. For the truss problems, it's needed because you need to be able to calculate all those transformation coefficients. You have local x prime, y prime, z prime. You need to be able to take the components and do the cosines of all those things. So that's why it's needed. And these, if you see, are more or less random. The way you can create those values are by actually just going to node I to node j. That gives you a vector in the direction of the element. Pick any other random vector. And if I take any other random vector and take a cross product of that with this vector along the direction of the element, what do I get? Cross product of any random vector with a vector along the element. I would get a vector that is perpendicular to the element, right? So that perpendicular direction allows me to specify an orientation which orientation that element has, which is all given in this file. There are boundary conditions and loads that you can very easily see. And I don't think I have time to run that problem, but I'll let you guys play with that code. And next time, I'll finish out the three-dimensional frames. And next week, Dr. Liu will do some SAP examples and a review for the final. All right, so see you all on Friday. Pineapple.